We have discussed the measurement of commuting observables. We saw that these measurements are compatible with each other. This is the reason why we call them as compatible observables. Okay? We can now talk about non-commuting observables, which we'll call as incompatible observables. We have seen that compatible observables are observables that actually commute. Right? And we have seen that when observables commute, when two observables commute, then they have a common set of or a complete set of simultaneous eigenkets. All right, they have a complete set of common eigenkets or simultaneous eigenkets. Okay, simultaneous eigenkets. And we actually saw that this is the reason why the measurement of one observable does not interfere or does not destroy the information regarding the other observable. Right? So when two observables commute, since they have a complete set of simultaneous eigenkets, the measurement of one observable will not destroy the information regarding the other observable. And this is what we have discussed in the case of compatible observables. Okay. We can now turn to incompatible observables. As we said, incompatible observables are observables that do not commute. Right? These are observables that do not commute. Or we can say that AB minus BA is not equal to 0. Right? Now, the important thing about incompatible observables is that they do not have a complete set of simultaneous eigenkets. Right? They may have a few simultaneous eigenkets, but they won't have a complete set of simultaneous eigenkets. Right? So incompatible observables are those observables which do not commute and which do not have a complete set of simultaneous eigenkets. Okay. Now for this reason, when you make measurement of one observable, it can destroy the information regarding the other observable. Right? That's the reason why we call them as incompatible observables. Okay. First, let's show that if two observables do not commute, then they don't have a complete set of simultaneous eigenkets. Okay. Now, one way to prove this is to assume the converse to be true. So we'll assume that if these observables are non-commuting, then they actually have a complete set of simultaneous eigenkets. All right. We'll assume this, and then it will lead to a contradiction, which means that our assumption is wrong. Okay. That's how we are going to prove this. So let's assume that there exists a complete set of simultaneous eigenkets for these observables A and B. All right, and A and B do not commute. Right. So let's go along with this assumption and let's label these common eigenkets by eigenvalues of observable A and eigenvalues of observable B. All right. So we'll label the common eigenkets as ket A prime B prime. Okay, in such a way that A acting on ket A prime B prime is the corresponding eigenvalue multiplied by ket A prime B prime, and B acting on ket A prime B prime is equal to B prime multiplied by ket A prime B prime. Okay, so I hope it's clear what we are doing. All right, the first step is that we are starting with incompatible observables, all right, or non-commuting observables, and we are assuming that they actually have a complete set of simultaneous eigenkets. Okay, and we label these eigenkets as ket A prime B prime. All right. So these are the corresponding eigenvalue equations. Right. Now let's find AB acting on ket A prime B prime. Right. So we'll use these eigenvalue equations. This means that B acting on ket A prime B prime is, okay, I'll retain this A here. B acting on ket A prime B prime is actually B prime ket A prime B prime. Right. Now this is a number, it's an eigenvalue. We can take it to this side. So this is B prime A acting on ket A prime B prime. All right. Now we assumed that this is also an eigenket of observable A, which means that this is equal to B prime A prime ket A prime B prime. Okay, so this is A B acting on A ket A prime B prime has to be B prime A prime multiplied by ket A prime B prime. Since these are numbers, we can simply write this as A prime B prime multiplied by ket A prime B prime. Okay. So AB acting on ket A prime B prime is equal to A prime B prime multiplied by ket A prime B prime. Right? If they have a complete set of simultaneous eigenkets. Okay. So this is what we did. We first assumed that we have got two observables which are incompatible or non-commuting. Okay. Then secondly, we assumed that these observables have a complete set of simultaneous eigenkets labeled as ket A prime B prime. Right. And from here we found AB acting on ket A prime B prime has to be equal to A prime B prime multiplied by ket A prime B prime. Okay, now we can find BA acting on ket A prime B prime. Right, now A acting on ket A prime B prime is A prime multiplied by ket A prime B prime. It's the eigenvalue equation. Okay, now this A prime is a number. I can take it to this side and I have got A prime multiplied by B acting on ket A prime B prime, and using the second eigenvalue equation I can write this as A prime B prime multiplied by ket A prime B prime. Okay, so what do we have here? We already had AB ket A prime B prime, which is this, right, is equal to BA ket A prime B prime. Both are the same thing, right? Both give us the result A prime B prime multiplied by ket A prime B prime. Okay, so from here we see that if these non-commuting observables have a complete set of simultaneous eigenkets, then we can write AB is equal to BA, or AB minus BA is equal to 0. In other words, A comma B, commutator of A comma B equal to 0. Right? But this contradicts our first assumption that we are dealing with non-commuting observables. Right? So you cannot have them as non-commuting observables and still have a complete set of simultaneous eigenkets. That will lead to a contradiction, right? Which means that we cannot, if two observables do not commute, they cannot have a complete set of simultaneous eigenkets. Okay, I hope this is clear. All right, so we can say that in general, a ket like ket A prime B prime labeled by eigenvalues of two incompatible observables, right? So we cannot label a ket by the eigenvalues of two incompatible observables. It does not make sense for incompatible observables. If you want to be able to do this, then the observables have to be compatible, right? Incompatible observables do not have a complete set of simultaneous eigenkets. Okay, so we have actually shown that non-commuting observables do not have a complete set of simultaneous eigenkets. Okay. Now there's an interesting exception. It may happen that there exists a subspace of the ket space such that this relation is actually satisfied. Right? This means that we might be able to find some kets for which this relation is satisfied, even though AB is not equal to BA. Right? AB in general may not be equal to BA, but there could be some kets for which this relation is actually satisfied. Okay. Alright, so that's what we say here. It may happen that there exists a subspace of the ket space such that this relation holds for all elements of this subspace, even though A and B are incompatible, even though A and B do not commute. Alright, so an example comes from the theory of orbital angular momentum. So there is a state called the S state corresponding to 0 orbital angular momentum, or L equal to 0. Right? Now in this state, right, this state is a simultaneous eigenket of both Lx and Lz with eigenvalue 0. Right? If either Lx or Lz is non-zero, then we cannot have L equal to 0. It won't be a zero angular momentum state, or it won't be an S state. Okay. So this S state is actually a simultaneous eigenket of Lx and Lz with eigenvalue 0 for both operators. Right? So the subspace here is one dimensional because there's just one ket. There's just one ket for which there's just one ket which is a simultaneous eigenket of both Lx and Lz. Right? Not the entire vector space, but only one ket in the entire vector space. Okay. So what we can say is that if AB, or if A and B do not commute, then they cannot have a complete set of simultaneous eigenkets. Okay, they cannot have a complete set of simultaneous eigenkets. They could have a few simultaneous eigenkets, just like this, just as we saw here, but they cannot have a complete set of simultaneous eigenkets. This means that every eigenket of A cannot be an eigenket of B also. All right, there could be some eigenkets of A which are also eigenkets of B, but this won't be true for every eigenket. Right, so that's what we mean when we say that they cannot have, or A and B cannot have a complete set of simultaneous eigenkets if they are incompatible. Okay. We already encountered some of the peculiarities associated with incompatible observables when we discussed sequential Stern-Gerlach experiments. Okay. So by now we know that these components of spin, right, Sx, Sy, Sz, etc., do not commute among themselves. Right? We know that, for example, Sx with Sy is not equal to 0, which means that they are incompatible. Or we can say that Sx with Sz is also not equal to 0, and Sy with Sz is also not equal to 0. All these are mutually incompatible observables. Right? And we have seen some of the peculiar things that happen with these incompatible observables. For example, right, let's just revise this. If we had a beam characterized by Sz plus, okay, and if I pass this through an Sg z hat apparatus, I know that there will be only one output corresponding to the eigenvalue plus h bar by 2, right, with a beam characterized by ket plus. There's only one output of the SGZ hat apparatus, that's a beam characterized by ket plus or ket SZ plus, okay, or characterized by the eigenvalue plus h bar by 2. All right, this is fine. Okay, but what happens if I take a beam characterized by ket plus and send it to an SGX hat apparatus? Right, then I'll get two beams here, one corresponding to Sx plus and the other characterized by Sx minus. Right, now if I send this to an SGZ hat apparatus, I'll get two beams. I'll get one beam corresponding to ket plus and another beam characterized by ket minus. All right, let me block this here. Right, so what happens here? I have measured the x component of spin, right, and it has destroyed the previous information regarding Sz. Right, now before, if I don't include this SGX hat apparatus here, this is the result I get. Right, the information is still there. If I pass it through SGZ hat any number of times, I'll always get only beams characterized by ket plus or beams characterized by eigenvalue plus h bar by 2 along the z direction. That's fine. All right, but before passing this beam through SGZ hat, if I choose to measure the x component of spin, right, if I choose to measure the x component of spin, then this beam actually picks up a component along the Sz minus direction also. Right, in other words, the measurement of Sx, has destroyed the previous information regarding Sz, regarding the observable Sz. Right, the reason is that they are actually incompatible observables. They are incompatible observables. All right, so the measurement of one observable will destroy the information, or it will mess with the information associated with the other observable. All right, if these are incompatible. These things we have actually seen. All right, now let's have a more general discussion of these kinds of effects. All right, let's discuss it more generally. Let us consider the sequence of selective measurements shown here. Right, so in this sequence of selective measurements, we have got three measurement devices. The first measurement device measures an observable A. All right, the second measurement device measures observable B. The third one measures observable C. All right, so these are denoted as devices A, B, and C. All right, now we know what happens during a measurement. If you start with any state and make a measurement of an observable, say A, after the measurement, the state changes to one of the eigenkets of this observable. Right? That's what's happening. Right? So from the first measurement device, we don't know the state of the electrons, for example. Right? We don't know the state of the electrons entering measurement apparatus A, but we know that the states of the electrons coming out of the measurement apparatus, right, are eigenkets of observable A. Alright, so the output of this device are eigenkets of observable A, and I choose a particular eigenket, say ket A prime, and block all others. Alright, so I have prepared some electrons in the state ket A prime using the first filter. Right, this arrangement is called an A filter. I think we have already discussed this term filter. Right, and the second measurement device takes in electrons which are characterized by the state ket A prime. Right, and we know that a measurement of B will change it into one of the eigenkets of B. Right, so we'll again choose one of the eigenkets and block all others. All right, we'll choose only one particular eigenket and block others. Right, so this is a B filter. All right, and in the third one, again we'll block everything else and choose one particular eigenket of observable C. All right, so the first A filter selects some particular ket A prime and rejects all others. The second B filter selects some particular ket B prime and rejects all others. And the third filter selects some particular ket C prime and rejects all others. Right? So this is our first experimental arrangement. All right. Now, the question that we are trying to answer is, right, what's the probability that I'll end up with ket C prime? What's the probability that I will end up with ket C prime if I start with ket A prime? All right, so the first apparatus is just used to prepare the electrons or the systems in a particular state ket A prime. All right, so after this filter, I've got a beam which is characterized by ket A prime. All right, I may have a beam of electrons, for example, which are all characterized by ket A prime. So I have prepared some systems in the state ket A prime. All right. So now the question is, I'm starting with ket A prime. What's the probability that I will end up with ket C prime after these things happen? All right, or in this particular experimental arrangement. All right. So in between, we are making a second measurement here. We are making a measurement of observable B. Then what's the probability that I'll end up with observable C prime? Sorry, ket C prime, not observable C prime, ket C prime. All right. Or in other words, what's the probability that I'll end up with an eigenvalue C prime of the observable C? Right? That's the right way to put it. What's the probability that I'll end up with eigenvalue C prime of the observable C? Right? And we know that ket C prime corresponds to the eigenvalue C prime. Right? That's the notation that we have been using. So let's see how we can calculate, or what quantum mechanics says about this probability. Okay. We are interested in the probability of obtaining ket C prime when the beam coming out of the first filter is normalized to unity. Okay. So let's say that this beam is characterized by a unit ket. Let's say that ket A prime is a unit ket. In other words, we can have ket A prime, sorry, bra A prime, ket A prime, or bracket of A prime is equal to 1. Right? Then we say that it's normalized to unity. Right? So given that this is a normalized ket, what's the probability that I will end up in a state ket C prime? All right. So if I start with a normalized ket A prime in this experimental arrangement, okay, what's the probability that I will end up with ket C prime? That's the question. All right. So I can write this as probability for ending, all right, or for obtaining ket C prime in the end, right? This probability, right? So we see that ket C prime will be obtained if two things happen, right? Two things have to happen. First, ket A prime has to change to ket B prime, and then ket B prime to ket C prime, right? So two things has to happen for us to get ket C prime, for us to obtain ket C prime after a measurement of C, right? So this is equal to the probability that first ket A prime changes to ket B prime and under a measurement of observable B, okay, and we need these two things happening, right? And ket B prime changing to ket C prime under the measurement of observable C. These two things has to happen. So we know from the basic rules of probability that P of A and B is equal to P of A multiplied by P of B. All right, P of A and B is equal to P of A multiplied by P of B. Right? Because these two things has to happen. These two things have to happen. All right. So we have to, in order to get the total probability, we have to multiply these individual probabilities. Okay. Now we know from quantum mechanics, postulates of quantum mechanics, how to calculate this probability. All right. So first we need to calculate the probability for ket A prime to change to ket B prime. Right. So usually when we write quantum mechanical probabilities, in such cases we start on the right. Right. So we start with ket A prime, we start on the right and go to the left. Right. This is how we usually write it. So we have got ket A prime. All right. What's the probability that you'll get ket B prime? It is bra B prime. So I start with ket A prime. What's the probability that I'll get ket B prime after the measurement of B? The probability is obtained by taking the component of ket A prime in the direction ket B prime, or by projecting ket A prime in the direction of ket B prime. Alright, this would give the expansion coefficient, and the modulus square of this will give you the probability of measuring probability of obtaining ket B prime starting with ket A prime. This is the basic postulate. This is the basic probability postulate. So what is this? This is the probability of starting with ket A prime and reaching ket B prime. All right. Now we need to multiply this with the probability for starting with ket B prime and reaching ket C prime. All right. So this again can be calculated with the same rule. I start with ket B prime. Okay. And I need to get ket C prime. So I project ket B prime onto a direction ket C prime, and then I take the modulus square here. All right. So these two things has to happen. First, ket A prime should change to ket B prime under a measurement of B, and ket B prime should change to ket C prime under a measurement of C. Okay. So the total probability would be the product of these individual probabilities. Right? That's what we have written here. Okay. So this is what we mean, because the probabilities are multiplicative. We have the probability of obtaining ket C prime is, first you start with ket A prime. What's the probability of obtaining ket B prime? That's given by the modulus square of the projection of ket A prime in the direction of ket B prime. Right? And then you have to multiply to this the probability that you get ket C prime starting with ket B prime. Right? This is obtained by taking the projection of ket B prime onto a direction of ket C prime and then finding the modulus square. Right? So this is the multiplication of two different probabilities. Okay. I hope this is clear to you. Right? So if not, think about it a little bit. Right? It's not too difficult. So this is, what is this? This is the probability of starting with ket A prime and obtaining ket B prime. Right? And what is this? This is the probability of starting with ket B prime and obtaining ket C prime. Right? So if I multiply these two probabilities, I'll get the probability for starting with ket A prime and obtaining ket C prime. Okay. Here is what we did. Okay. We calculate the probability for obtaining C prime if I start with ket A prime and go through ket B prime. Right? So what's the probability of obtaining ket C prime after going through ket B prime? That's the probability that we calculated. So this is the probability that we have given here. This is equal to the probability that A prime or ket A prime changes to ket B prime multiplied by the probability of ket B prime changing to ket C prime. Right? That's what we have written here. We said that we have to read this from the right. Okay. Now this is for just one route. Right? This is the probability for reaching ket C prime going through ket B prime. Right? Now you can calculate the probability. You can calculate the probability for going through another route. Again, you start with ket A prime and go to ket B double prime, right? And then to ket C prime. This is another route, right? So this would be modulus square of, you start with ket A prime, find the probability of going to ket B double prime first, right? And then you find the probability for going from B double prime to C prime. Okay, this is going through the second route. All right. You could also calculate the probability for going through a third route. All right. So if you are allowing all these routes, right, one by one, okay, or you could take a large number of experimental arrangements like this, right? One in which ket B prime is only allowed, and the second in which only ket B double prime is allowed, etc. Okay, you could take a large number of apparatus that we can, a large number of the same experimental arrangements. All right. For example, let me try to explain it here. We start with a ket A prime, right? In the first apparatus, I sent it to a measurement apparatus for B or a filter, right? So filter includes the measurement apparatus and blocking of all other beams, right? So I have a ket. Let me denote it as ket B1 here. Okay, so the output of this filter is only ket B1, right? And then I make a measurement of C to obtain. Okay, here I'm blocking all other outcomes, all right? So this is the final state, no change in that. This is the final state that I want. This is the initial state I started with, all right? So in between, I'm allowing it to go through ket B1 or ket B2 or ket B3. So the second apparatus would look like this. I again start with ket A prime, right? And here I block ket B1, right? I choose only ket B2. Okay, and then make a measurement of C on this and look at the probability for calculating ket C prime. right? All other beams are also blocked. All right. Similarly, in the next experimental arrangement, I'll have get B3 allowed and everything else blocked. All right. So you can imagine of having a large number of experimental arrangements like this. All right. And then we ask, what's the total probability of that you get C prime if I start with get A prime? Okay. If I start with get A prime, what's the total probability? So we see that starting from get A prime, I can reach get C prime through get B1 or through get B2 or through get B3, etc. Alright, so we'll basically use this rule. If you want to calculate the total probability, okay, P of A or B, right, this is equal to, this is the equation for probability, P of two events A or B, or let's say, let's say X or Y, all right, because A and B we have used here. The probability for X or Y is equal to P of X plus P of Y. All right. So we are asking this following question: what's the probability that you reach get C prime through get B1 or through get B2 or through get B3, etc. This is the question that we are asking. All right. So you have to take each of these probabilities and add them to get the total probability. Okay. I hope this is sufficiently clear. All right. So now let us sum over B prime to consider the total probability for going through all possible B prime routes. Okay, so operationally this means that we first record the probability of obtaining C prime or the eigenvalue C prime with all but the first B prime route blocked. This means that only the first B prime route is allowed in the first experiment, all right? And we repeat the procedure with all but the second B prime blocked, all right? Then we allow the second beam and then carry out the experiment a large number of times, all right? Then we block everything except the third B prime, right? Except the third B prime, and then carry out the experiment. And then we, what do you say, block everything except the fourth one, and then carry out the experiment, right? And then we can calculate the total probability by the usual rules of finding the total probability. Okay, that's why we are summing over all the possibilities. Okay, so the basic idea is that we are finding the probability for probability that starting with A prime, you reach B prime. Let me, you reach get B prime, B1 first. Okay, let me write as B1 first and C1, C prime. All right, or you start with get A prime, reach B2 or reach get C prime. Okay, the initial state and the final state are the same. All right, we are just allowing various routes. All right, so what's the probability that you reach get C prime through B2, right? So this is the probability that we are calculating. Or you could have get A prime to B3 and then to get C prime. Okay, this would be the total probability, all right, or etc. So this is P of X or Y or Z, etc. Right, as many routes that are available. So you have to add all these probabilities, right? So you take one of these probabilities and add all such probabilities, all right? You add the probability for each, the probability for reaching get C prime through each of these routes, right? So that's what I mean by putting a summation over B prime here. Okay, so I take this probability. This is the probability for reaching get C prime through get B prime, right? If I want the total probability, I take this probability and then I add corresponding to the probability for reaching get C prime through all the different paths. Okay. Now I hope this expression is clear now. Let me continue. Now this get B prime A prime, right? So this can be written as, this is get C prime B prime, modulus square of get C prime B prime. This I can write as get C prime B prime multiplied by, so this is bra C prime B prime multiplied by bra B prime C prime, the complex conjugate, right? This is a number. This is the corresponding complex conjugate, right? Similarly, this can be written as bra B prime get A prime multiplied by its complex conjugate. Its complex conjugate is bra A prime get B prime. Okay, and you have got the summation over B prime. Right, so this is written here in a slightly rearranged matter. I've got get C prime B prime, bra C prime ket B prime here, that is this, and I have got bra B prime ket A prime here, that is this term, all right, and this bra B prime ket C prime, that appears here, all right, and bra A prime ket B prime appears here, all right. So this is how I get all these terms. Okay, it doesn't matter since these are numbers, all right. It doesn't matter in which order you multiply them, right? We have just written it in a convenient manner, that's all right. In the second arrangement, the B filter is absent or not operative, which means that you are not making a B measurement. In this arrangement, you are not making a B measurement. So the question is this: what's the probability that if I start in ket A prime, I'll get ket C prime? So what's the probability for getting ket C prime if I start with ket A prime and measure C on it? We know how to calculate these probabilities. So we start with ket A prime and we need to get ket C prime. So you project ket A prime onto ket C prime and take the modulus square. This is how we calculate the probabilities. Okay. Now we can insert an identity operator in here. So this thing can be written as modulus square. Okay, I have got a ket C prime here. So in order to introduce this identity, I'll introduce the identity in this form. I'll write sum over B prime ket B prime bra B prime is equal to the identity operator. Okay, this is the identity operator that I am going to insert in here. So there's a sum over B prime. I've got this bra C prime here, and I've got ket B prime bra B prime, okay, and ket A prime, this ket A prime, right? The modulus square is still there. Okay, so what have I done? I've just introduced an identity operator in between here. All right. So this is the modulus square of a summation. So what we do is that you take this entire term and multiply it with its own complex conjugate. All right. But this entire term involves a summation over B prime, okay, or summation over all the B alternatives, if you like. All right. So the complex conjugate also will involve a sum over B prime. All right. But since we have used the summation index B prime here, I'll use a different index. I'll call it as B double prime. Okay. So this modulus square can be written as, okay, this on the one hand, I've got sum over B prime, okay, bra C prime, ket B prime, bra B prime, ket A prime. All right. That's this term multiplied by its complex conjugate. Right? So its complex conjugate, in order to write the complex conjugate, since this is a summation of terms, I should use a different summation index. So I'll use the different summation index here, sum over B double prime. All right, if I use the same summation index, I'll be missing some terms. All right, you can check this. Right, so if you want to square a sum of terms, you have to use two different dummy indices. Okay, so that's why I'm using a different dummy index here, and then the complex conjugate of this thing. All right, what's the complex conjugate of this thing? I'll start with here. What's the complex conjugate of this? This is equal to bra A prime. All right, here the dummy index is B prime. Here the dummy index is B double prime. So this ket A prime becomes bra A prime. The dummy index I'm using ket B double prime. Okay, now this becomes bra B double prime. Okay, bra B double prime and ket C prime. Okay, so instead of modulus square, I have written as the number multiplied by its complex conjugate. Okay, so that's what we have here. The summations I have written together, sum over B prime, sum over B double prime. And what do I have? I have got bra C prime, ket B prime, that's this term, and bra B prime, ket A prime, that's here, right? And then I have got bra A prime, ket B double prime, that is this, and bra B double prime, ket C prime. Right? This is the probability for obtaining C prime if I start with ket A prime. All right. Remember that here we have not carried out a B measurement yet. Okay. So we don't carry out a B measurement in this case. In between, there's no B measurement. All right. We have just inserted the eigenkets of B using this uh, completeness relation, right? So the interpretation of this thing is that we are still assuming that you can start with get A prime and it goes to all possible B primes, all right? It goes through all possible routes before reaching get C prime, all right? But I don't make a measurement in between. That's the only difference here from the first arrangement. In the first arrangement, I am making a B measurement in between. Here, I am not making a B measurement, right? But still, we can assume that since get A prime, right, since get A prime can be written as a linear combination of get B primes, okay, we can write get A prime as a linear combination of all the eigengets of B, right? So we can say that get A prime is spread out over the eigengets of observable B. You can say that it's spread out over the eigengets of observable B, right? So you could imagine a beam starting in the state get A prime. Okay, you could also imagine it as a combination of so many get B primes. Right, that's what we have done here. You could either call it as get A prime. Okay, but get A prime quantum mechanically can be considered as a linear combination of so many get B primes. Okay, so let's say sum over B prime. Okay, and then I may have some expansion coefficients. I will have some expansion coefficients for each of the eigengets. All right. So this expansion coefficient that I denote as CB prime here are the same as these things. All right. Bra B prime, get A prime. Right. So get A prime is actually, if you can actually write it in this form quantum mechanically. All right. And the interpretation is that get A prime is constitutes of so many get B primes. All right. It consists of so many get B primes. All right. Only difference with the first arrangement is that I'm not making a measurement in between, right? And in that case, the expression for probability is this, right? We calculated the quantum mechanical probability for ending up with get C prime if we start with get A prime, all right? And we calculated the probability in two separate cases. In the first case, we calculated the probability for ending up with get C prime if we start with get A prime and make an intermediate B measurement. All right. So if we make an intermediate B measurement, we found that the probability for ending up with get C prime is given by this expression. All right. Now, if you don't make an intermediate B measurement, you see that we get a different expression for probability, and it is this. All right. Now, if you remember the calculation that we actually carried out, right, you'll see that in this case we actually first found the probability for passing through each of the B prime and then added all the probabilities. All right. In the second case, we actually added the probability amplitudes for passing through each of the get B primes. All right. Each of the get B primes. All right. So in this case, we added up the probability amplitudes first, found the total probability amplitude in this case, and then found the modulus square. In this case, we found the probabilities first for passing through each get B prime, and then added up all the probabilities. All right. And this will in general give different answers. Right? This is why so many weird things are happening in quantum mechanics. All right. Because when we add probability amplitudes can be positive, negative, complex, anything. Right, and these things can cancel each other. But when you add up probabilities are between 0 and 1, or it could be 0 or 1 in the extreme cases. Right. So when you add these positive numbers, they never cancel. All right. So the reason why we get sort of interference phenomena, right? We have discussed the double slit experiment, and the reason why we get interference phenomena, etc., over there is because certain probability amplitudes get cancelled. All right. Okay, so notice that expressions 2 and 3 are different. This is 2 and this is 3, right? This is remarkable because in both cases, the pure get A prime beam coming out of the first filter can be regarded as being made up of the B eigengets, right? In both cases, get A prime can be regarded as being made up of the B eigengets. So in other words, we can expand get A prime in the B eigengets. Right? These are the expansion coefficients and these are the basis gets. Okay, base gets. Right? So the sum is over all possible values of B prime. Right? The crucial point to be noted is that the result coming out of the C filter depends on whether or not B measurements have actually been carried out. In the first case, we experimentally ascertain which of the B eigenvalues are actually realized. Okay. In the second case, we merely imagine ket A prime to be built up of the various ket B prime, right? Like this. Ket A prime is equal to sum over B prime, ket B prime, and the expansion coefficients, right? Bra B prime, ket A prime, all right? Okay. So put in another way, actually recording the probabilities of going through various B prime routes makes all the difference, even though we sum over B prime afterwards. Okay. Here lies the heart of quantum mechanics, right? So this is probably the reason for every weird quantum mechanical phenomena, right? Most of the weird quantum mechanical phenomena, the kind of things that we see in the double slit experiment, right, can be explained by this kind of reasoning, all right? Under what conditions do the two expressions become equal? Right? So we had two expressions before. Okay, one for the case where you make an intermediate B measurement, and the second for the case where you do not make an intermediate B measurement. All right. Now it's easy to show that if the observables actually commute, if the observables are actually compatible, right? Either if A and B are compatible, or if B and C are compatible, okay, in the sense that their commutator is 0, then you can show that both these expressions, both the probabilities, both the predicted probabilities will become equal, right? This means that the situation that we have described is characteristic of incompatible observables, right? It's a characteristic of incompatible observables, right? Now it is easy to show this, right? So starting with the fact that the commutator of A and B is 0, you can show that both expressions give the same result, right? In fact, you can show that the second expression, right? If you start with the second expression, the expression corresponding to the second experimental arrangement, where we do not make an what do you say? Where we do not make an intermediate B measurement, right? So if you take that expression into equation 3 in the previous slide, okay, and you demand that the commutator of A and B is equal to 0, you will see that equation 3 will reduce to equation 2. Okay, you can actually see this, right? Now I leave it as an exercise for you to show this. It's not very difficult. You just remember that if A and B commute, then they have a complete set of simultaneous eigenkets. So if they have a complete set of simultaneous eigenkets, that means that an eigenket of A is also an eigenket of B, right? Now using this and the fact that the eigenkets of Hermitian observable or Hermitian operator are orthogonal, right, or orthonormal, if you like. Right? We can choose an orthonormal set. Right? Using this fact, you will see that. So you just use the orthonormality relation, and you'll see that expression 3 will reduce to expression 2. Right? So I leave it as an exercise for you to do. Right? So this is, of course, in the absence of degeneracy. In the case of degeneracy, it's a little bit more complicated, but the basic logic is the same. Okay. So the peculiarity we have illustrated is characteristic of incompatible observables. All right. Now you are welcome to analyze different situations using the techniques that we discussed in this class. All right. For example, you could calculate the probability for ending up with Sx plus if you start with state Sx plus. All right. And you can do this in two cases. You could do this if I make an intermediate Sz measurement and if I don't make an intermediate Sz measurement. All right. So you can just repeat the steps that we carried out in this class and see how these things actually work. All right. You can do this because we already know the expression for get Sx plus in terms of the eigenkets of Sz operator. Right. So this analysis will be quite enlightening to you. Right. You could, in the second case, you could find find the probability for ending up with Sx minus if I start with get Sx plus. Again, in two cases, if I make an Sz measurement in between and if I don't make an Sz measurement in between. All right. So if I don't make an Sz measurement in between, we know that this probability is 0. Right? But if you write it out in terms of the eigenkets of Z, you will see that you will get the same result and you will see that some of the amplitudes are actually getting cancelled. Right? So this will be quite interesting. Right? So try these things out. We had discussed the double slit experiment in the beginning. All right? If you're interested, you can analyze that case also. At least write down some of the expressions. Right? So in the double slit experiment, we had a source, right, and a pair of slits and a screen. All right? Now we see that there are two possible ways open for these electrons to pass, through. right? Now we could actually calculate the probability that an electron will fall at each point, right? If an intermediate measurement is made, like we said, we'll keep a video camera here, right? In that case, you will have to add up the probabilities, right? And if there is no intermediate measurement here, right, then you will have to add up the probability amplitudes, right? And this will cause all the difference. Okay, so if I make an intermediate measurement, I'll get a particular pattern, an intensity distribution of electrons on the screen, right? And if I don't make an intermediate measurement, if I don't have video camera here, I'll get a different, I'll get a different distribution. I'll get a different distribution of electrons on the screen, right? This distribution we called as an interference pattern. All right, and this can be analyzed using this technique. So this is source, and let's call this as slit 1 and slit 2. Okay, so we can ask the following question: what's the probability that if I start with this state, let's say ket S, corresponding to state of the electrons coming out of this source? All right, so what's the probability that if I start with ket S, I end up at a point X, also denoted as ket X? Right, we can ask this question, right? You see that there are two paths open here, so we can use the same techniques. I can say this, I can calculate the probability like this. You start with ket S, right? You first find the amplitude for it to reach the slit 1, right? And then find the amplitude to reach get point X from slit 1, right? So that would be given by projection of ket 1 on ket X. All right, this could represent any point on the screen. All right, you see that there is one more possibility. You could start with the source, go through slit 2, and end up at point X. Right, so if you add these things, you see that you are adding probability amplitudes. You'll see that some of the amplitudes actually cancel. At some points, the amplitudes cancel each other. At some value of X, some values of X, these amplitudes will cancel each other, and the electrons will not reach there at all. Right? But if I'm making an intermediate measurement here, I'll be adding probabilities, and these probabilities will not cancel each other. Right? And this is the reason why we have different patterns depending on whether we make an intermediate measurement or not. All right. So again, I leave it as an exercise for you to analyze these things. All right. And if you're interested in this discussion, you could read the third volume of Feynman lectures. All right. Feynman lectures in physics. I hope you're familiar with this. And the third volume deals with quantum mechanics. All right, and he has actually extensively discussed the double slit experiment using these kinds of expressions. All right, so you're welcome to read that if you have the time. All right, so with that, I'll conclude the discussion of incompatible observables. Thank you.